Okay, so welcome to another session of our reading group that we resumed after 2 weeks that I was on travel. And let me get everybody in. We'll see how many people we lose for the break. This is usually what happens. Something happened and people forget. Okay, so shall we just jump right in? Has anybody have any questions before starting? I need to put this in the chat.
Maybe should we kind of summarize where we were last time?
Yes, in fact, I can do this by looking at the index. So at the beginning, we saw that classical mechanics, Lagrangian mechanics, and Hamiltonian mechanics were not equivalent. And we looked at that and we saw that there was a difference between the kinematics and the dynamics. And then we saw that Lagrangian mechanics has this assumption of kinematic equivalence, that is, from the velocity and the position, you can recover the momentum and position. So you can recover the dynamics by looking at the kinematics. And then we started looking at Hamiltonian mechanics more closely. We did it for 1 degree of freedom, and we saw 12 equivalent characterization, which basically were all about determinism and reversibility. So we saw that Hamiltonian mechanics and like has this assumption baked in. And since previously we saw that Lagrangian mechanics is a subset of Hamiltonian mechanics, that every Lagrangian system is also a Hamiltonian system, then of course this assumption is going to be there in Lagrangian mechanics as well. Then we looked at multiple degrees of freedom of Hamiltonian mechanics, and we saw that the additional assumption that was needed was the independence of degrees of freedom, such that you can define a degree of freedom without knowing that you have a degree of freedom, and the total space is essentially the product of the two spaces. So the way that you count states, for example, the overall number of states is the product of the number of configuration of independent degrees of freedom. And then last time since there were these recurrent elements of differential topology, and which are going to be using now, we looked more closely at the notion of differential forms. And the idea is that a differential form is basically something that takes an infinitesimal parallelepiped and gives you back a number. So a two form takes two vectors and then gives you a number that is related to the area, to the rectangle. No, it's not a rectangle necessarily, a parallelogram that it's given by those two vectors. So that's more or less where we are, I think. Does that sum it up?
Yeah, sounds good.
And so today we're going to go and look at Lagrangian mechanics more specifically and see what that's all about. So today we are going to basically do the reverse engineering of the action principle and see what the action is, what the Lagrangian is, and all of those things. So I will share, as usual, the text so that people can follow the text as I see it. Okay, so let's get started.
Okay, so reversing Lagrangian mechanics. Now that we have a good geometric and physical feel for Hamiltonian mechanics, and that we have a general understanding of what the tools of differential topology describe physically, we will analyze Lagrangian mechanics more in detail. Conceptually, we already know that Lagrangian mechanics is Hamiltonian mechanics plus the assumption of kinematic equivalence. We will see that the flow of states in phase space admits a vector potential, and the Lagrangian is the scalar product between that potential and the displacement along the path. The principle of least action is geometrically equivalent to asking for paths that are always tangent to the displacement field. Moreover, the principle of least action is better understood as a property of Hamiltonian evolution, and the assumption of kinematic equivalence is only required to express the product between potential and displacement in terms of velocity instead of momentum.
Kinematic assumption revisited. As we saw in section 1.2, Lagrangian mechanics is the subset of Hamiltonian mechanics for which assumption kinematic equivalence is valid, which means Lagrangian mechanics is equivalent to assuming what's the R again?
Determinant reversibility.
Determinism and reversibility, independent degrees of freedom, and kinematic equivalence. For the first two assumptions, we found a host of equivalent mathematical, geometric, and physical formulations. Let's see what we can find for kinematic equivalence.
First of all, let us summarize the conditions we have already found. Hamilton's equations always impose that the velocity is a function of the state variables. Equation 1.9, so that's vi equals dtqi, which is partial pi of Hamiltonian. Fixed position, the Jacobian of the transformation is therefore the Hessian of the Hamiltonian, which is written in equation 1.91. Therefore, condition, at every position, the relationship between momentum and velocity is invertible and differentiable, and condition, at every point, the Hessian of the Hamiltonian is non-singular, hyperregularity of H, determinant of the Hessian is different from zero, are equivalent to each other. The non-singularity of the Hessian can also be understood as strict monotonicity of the derivative along momentum. Therefore, the Hamiltonian is twice differentiable and concave or convex. In momentum is another equivalent condition.
Note that the relationship between velocity and momentum is not just invertible, but differentiable as well. This may seem like an additional condition from kinematic equivalence, but recall that the dynamics is not in terms of points, but rather cells of phase space and density distributions. In order to express those geometric elements in terms of the kinematic variables, we must make sure that the Jacobian determinant of the transformation from state variables to kinematic variables is well-defined and non-zero. We have equation 1.92.
Yes, so the thing that I think is interesting here is that this is the Jacobian of the transformation that goes from position and let's see, position and momentum to position and velocity, right? So what happens here is that the position, when you have this transformation, the position is still the position. So the position is only going to be a function of the position. It doesn't change. So this term here is zero, right? Because you're changing the velocity to the momentum, but the position remains the position. So here, this is just going to be the Kronecker delta because the qi and the xi are the same thing, right? And here, you have no dependence on the xi with the pj because it's all going to be a dependent in terms of the qi, so you have a zero. So regardless of what these two things are here, now you have the determinant of this matrix, and so you only care about the product of the diagonals because the other non-diagonal term is going to be zero.
Should it be del bi vi in the last on the right hand side? Yeah.
No,
The
it's still here. You're still changing variables. You're going from v to p, and v and p are different.
Okay, so the Kronecker delta doesn't like act on
Oh, it's you're taking the determinant.
that? Okay.
So the Kronecker delta is the identity matrix. So
Okay.
the determinant is one.
Okay, yeah,
Right?
okay.
So
Yeah.
you see, this is the product of the determinant. You are not.
Yeah.
It's not the product of the matrices.
Got you. Okay, thank you.
So the Jacobian determinant of the change of variables then coincides with the Jacobian determinant of the relationship between velocity and momentum at constant position. Therefore, the following conditions are all equivalent to each other and to condition of invertibility, right?
Yeah.
So the Jacobian of the transformation between state variables and kinematic variables is non-singular. Densities over phase space can be expressed in terms of position and velocity. Areas and volumes in phase space can be expressed in kinematic variables. The symplectic form omega can be expressed in kinematic variables. And the displacement field S can be expressed in kinematic variables.
Right. So basically, the transformation between velocity and momentum has to be differential because what you care about are the densities, the areas, and the symplectic form and all of this. So if you had a transformation between velocity and momentum that were not differentiable, you wouldn't be able to express these things. So you wouldn't have good coordinates to which describe the system anyway.
What does the W stand for in WKE?
This one? No, this is
No, like WKE.
Oh, sorry, WK. So this is gonna be C. That this is gonna be weak kinematic equivalence.
Okay.
And you will see later that there is a stronger form in which the transformation not only is invertible but it's linear. And then we're gonna see and argue that that actually is the real way to take this assumption.
Okay. The insight is that differentiability between state variables and kinematic variables is required to be able to express the objects we use to characterize the deterministic and reversible dynamics. The only physical requirement then is to be able to express the dynamics in terms of the kinematics, which is exactly what assumption KE already requires. Should I continue or?
Sure.
On the physical meaning of the Lagrangian. A key problem is to understand what the Lagrangian represents physically. It is often introduced as the difference between kinetic and potential energy. However, this does not work in general. Take the Lagrangian for a particle charge Q under an electromagnetic field with electric potential V and magnetic potential A sub I. Yeah, and then we have an extra term that's not kinetic energy or potential energy.
Yeah.
The first term is clearly kinetic energy and the last clearly potential energy. But what about the middle term? It depends on velocity, so it would appear to be a kinetic term, but it also depends on the potential. It's both and neither. The characterization of Lagrangian as difference between kinetic and potential energy then works for some systems, but not in general, and it is best abandoned.
Another problem in understanding what the Lagrangian represents is that it is not unique. Now, a similar problem exists for the Hamiltonian in the sense that we can sum an arbitrary constant to any Hamiltonian without changing the equations of motion. However, the degeneracy for a Lagrangian is far worse. For example, let fxit be an arbitrary function of position and time. We can set some Lagrangian L prime equals to original Lagrangian plus some partial xi of xit vi plus partial t of xit, equation 1.94. We can see how the Euler-Lagrange equations 1.3 are affected. Equation 1.95.
Yeah, this is just basically taking this and substituting. So let's see if I can pick up the parts. Okay, so this would be the term for the original Lagrangian, right? And now you have the different partial derivative with the f's, and then there is the total derivative in time with the original thing and the f as well. And I think let's see if I can reconstruct the trick. So you take these two parts and you get hi Mim. You get the original equation, right? And now you have this part is this part, and this you're just using the chain rule on the derivative in time. right? So you're doing the derivative in time of like you imagine that this whole thing is a function of position, velocity, and time. So you first do the change in position, and then you do the change in time. The dt is 1. The dt xj is just the velocity. And now you basically have these two terms that are exactly the same thing and they cancel out. So you're basically making a modification of the Lagrangian, but then when you do the Euler Lagrange equation, the two sides of the Lagrange equation essentially cancel out.
Right, and you end up with the same Euler, the original Euler Lagrange equation. And
Say
that
again?
is you end up with this, like the same equations on the original Lagrangian.
Exactly, yes. You see, you get the same equation as if you didn't introduce the other term.
That is, the equations of motion given by L prime are the same as the ones given by L. Therefore, the actual value or the difference of values of the Lagrangian is physically meaningless. This makes the question even more puzzling. What is the Lagrangian?
The extended phase space. Given that we have a good understanding of Hamiltonian mechanics, let's work on the equations that link the two. We have, and here we have the Legendre transform of the Hamiltonian being the Lagrangian, and then we expand velocity in terms of being the derivative of position, and then we just add multiply by 1 basically the Hamiltonian and write that as the derivative of time, and then we can rewrite that in this way. Okay.
Right, we're basically adding a 0 in the middle so that we also have the derivative of p in time.
The Lagrangian then can be understood as the scalar product of two vectors. The second one is the displacement along the path. However, it is the displacement not just in position and momentum, but over time as well. The correct setting to understand Lagrangian mechanics then is phase space extended by the time variable. If we redefine psi sub psi I, yeah, as to include the time variable, we have now this displacement field. We can then define the new vector theta sub A in terms of its components. We also need to generalize the symplectic form to the extended phase space. Looking at equation that was
so HMG is
that was Hamilton.
Yes, it was Hamilton's equation.
Okay. So the idea is to put the gradient of the Hamiltonian in the time component.
Exactly.
Okay, if we set, what's that?
Right. So in the space and momentum, we have what we had before. And then in the time part, we have the derivatives of the Hamiltonian with respect to position and momentum.
Okay, and then we have equation 199.
Right. So now we take the displacement field and contract it with the first part of the symplectic form. So you have the QI, QI, PI, PI, T, and T. And then we just go and find the elements here. So QI is 0. So this term goes away. The PI, QJ is this one, actually this one, P and Q. And so you get minus the Kronecker delta. So you basically have a minus, and then you change this I in the J. And then you have the ST, and the TQJ is this part, so it's minus partial QJH, which is here. And now ST again is going to be 1 because it's dt dt, And so you just have minus SPJ minus the partial QI, QJH. And if you put this on the other side, that's one part of the Hamilton's equation. You do the same thing for the other side. Now this is going to be the part that is J. This is the part that is going to get the Kronecker delta. So this SQI becomes SQJ. And again, you have TPJ, which is this term here. And you get, again, the minus ST partial PJH. The ST is 1. And again, you get these two equal to 0. And now you take this, put it on the other side. That's the other part of Hamilton's equation. And the last bit is basically just a constraint. What happened is that the TT now is 0. So you just have these QIT and PIT. So this pulls out the derivatives of H. But then from previous equations, you know that the SQI, right, from here, you know the SQI is partial PIH. And from the other equation, you know that SPJ was partial minus partial QJH. And now this is just the product of the two terms. These terms are the same, and it's equal to 0. So basically, the previous equation already implied that this is going to be 0.
Okay. This means that on the phase space extended by time, Hamilton's equation become so when we contract the displacement field with the symplectic form, we get 0.
Yeah. And you can see, like, if we go back here, right, this is what we had before. It's like this is the time component. So now you put this on the other side and you imagine this whole thing is equal to 0. It's because you're basically saying the time component and the other parts are going to be, put together.
Note that while the position and momentum components of the displacement field still perform a rotation, the time component does not. So we can't understand the displacement field as a rotated displacement, or it's not the displacement field, it's S sub A, after we act on it with the symplectic form.
Yeah.
Recall that, so basically, so recall that basically by taking this scalar product with the symplectic form in the middle, that quantified the number of states in the parallelepiped formed by the two vectors.
Yeah.
If that term is 0, then the parallelepiped does not identify states on an independent degree of freedom. For each vector VA, the covector V sub A identifies the direction that forms an independent degree of freedom with VA. If we only have position and momentum, we can see that you get the direction rotated by 90 degrees along each degree of freedom. If we extend phase space with time does not add a new independent degree of freedom. In fact, the direction given by the displacement field SI should give us no new independent states. There should be no direction VB in phase space such that so that would be is that just because we say that like the first part SA times omega AB should be 0, so there shouldn't be any
Right.
VB that
I'm going
has
in the
a
other direction. So I'm justifying why this thing should be 0. So
Okay.
I'm basically saying if I have the omega and I put two vectors, I know that those two vectors form an independent degree of freedom. because they give me some configurations. And then I'm saying, well, if I have the displacement field and the displacement field is going forward in time, and time does not add any new degree of freedom, I should not find any other vector that makes an independent degrees of freedom with the direction where the system evolves in time.
Okay.
And so this expression should always be zero, no matter what VB is, and that it means that this part must be zero.
In other words, sub B must be zero, and this is what the previous equation says.
So
Okay.
this is where, if we had pictures, probably things would be a lot more clear, right? So if you take, let's say that I have the three axes, right? Position, momentum, and time, right? And if I take position, right, I can find another degree of freedom such that I go here and I find something, and these are configurations, and they define something. If I take the displacement field, right, and so I'm moving forward in time, the point is that I should not find any other vector that would form an independent degree of freedom with that motion, right? And so while the vector exists, if I try to make a parallelepiped with any other thing, and I ask, tell me how many states do I have in that very parallelepiped, the answer should always be zero. This is where we're very always anchored in the geometry. We're thinking of the geometry of R2, that all the areas are always areas, and so they have something. While the geometry here is counting states. So the fact that you have a parallelepiped doesn't mean that parallelepiped has states associated with it.
Okay. Potential of the flow, 1 degree of freedom case. We wrote the Lagrangian in terms of theta and blah, blah, blah. But we have yet to understand what theta A is. If we compare it to omega AB, we note that the first has the Hamiltonian as a component, while the second has its derivative. Given that omega AB is antisymmetric, it is a two-form. We may want to calculate the anti-symmetrized derivative of theta A, the exterior derivative. We have...
And this is just pure calculation. So you have to remember that theta A has these components, and then you basically plug them in. So this is just the expression of what all the components would be. And then the second step is just for all the theta q becomes pi, because those are the components. So you go there and you substitute them in all places. The other ones, the theta pi are zero. So you put all the zeros, and the theta t's are minus h. And so you just put all the minus h. So you basically have this. This is just substituting the components. And then you do the calculation. So if you're making a partial q for p, since these are independent variables, you get a zero. So all the things, all the terms that mix q's and p's are going to be zeros. And of course, all the terms that are taking derivative of zero are also going to be zero. Then if you have a p and p and q, right, these terms here, these p and p, are going to be Kronecker delta, because they're going to be one if and only if the I is equal to j, and they're going to be zero otherwise, because momentum along different components are independent variables. And so you get all these Kronecker delta here for when you have the derivative with respect to p. And then you get again, these are partial derivatives. So the partial derivative with respect to p is zero, because p and t are independent variables. and then the rest are just the derivatives. So you do this, and now you find that this first component is 0. This is going to be minus Kronecker delta. These are Kronecker delta. This is 0. So this is the symplectic form without the extended phase space. And then you see that on the other terms, you get the terms that we had before. And this part again simplifies because you're taking it first with the minus and second with the plus.
Can you scroll up a little bit?
Up?
Let's see the Lagrangian.
The Lagrangian.
Oh yeah, sorry. It's at the bottom of that page, 47. Oh no, up one.
Oh, sorry. I thought
Yeah.
that the bottom. Yes, yeah.
I mean the bottom of the next page, with the theta L equals.
Oh, this one.
Theta, yeah.
Yeah.
Okay. Okay, I can continue.
Yeah, we're going to see how it connects to the Lagrangian. Here, the only point is that we found the relationship between the theta A and the omega AB that we found before.
This means that the form omega AB is minus the exterior derivative of theta A. In other words, omega AB has a null exterior derivative and theta A is its potential.
Given that the extended phase space for a single degree of freedom is three-dimensional, we can use standard vector calculus to gain more understanding. In this case, we have theta A, which is just that, and the form omega AB.
Right, so this is the usual trick that you can do in 3 dimension, that a 2 form becomes a vector, right? So that you have the, like a magnetic field, right? If you did some, what's it called, special relativity, and you started putting the magnetic field in a form, you basically have this thing where you basically are scrambled the magnetic field in the 2 form like that. This is exactly what happens. So this would be the essentially the what's it called? This would be the axial vector, right? And this would be the oh, Madonna mia. Yeah, this would be the axial vectors and represented as a 2 form. So when you have a magnetic field, you can represent it also as a matrix like that.
Okay. Where epsilon ABC is the fully antisymmetric Levi-Civitas symbol, which returns the sign of the permutation of the variables. So for instance, epsilon QPT is equal to epsilon PTQ equal epsilon TQP equals 1, whereas TPQ, PQT, and QTP are minus 1.
Right. So this is basically the usual thing where you start with a permutation and you take the Q, you put it at the end, and then you take the P and put it at the end, right? That's sort of how it works. And this is the permutation where I went in the reverse order. And
Right.
so I do the same cycling, but in the reverse order.
Right. We have epsilon ABC, C. That's just the 2 form, which we said was the minus the external derivative of theta.
Yeah.
Which you write out, and then that gives you the displacement field as a vector, and you just write it as a, yeah.
And so this is basically S is the kernel of theta, right?
Yeah.
So this vector potential becomes, exactly like you have for the magnetic field. So this would be the magnetic field, and this would be A, the vector potential. In the same way, now this is the displacement field, and displacement field as a vector potential.
Right. Apart from the minus, this is the same relationship we would have between magnetic field, yeah, BI and its vector potential AI. Therefore, the same concept from vector calculus applies. As A is divergenceless, emits vector potential, and the flow of the displacement over a closed surface is 0. We can understand this as assumption DR, determinism and reversibility, implemented in the extended phase space. Moreover, we have the following relationship. which is that that's the 2 form over sigma, and then you have over sigma epsilon on the displacement. Okay.
So this is basically the triple product in 3 dimension. Like where you have 3 vectors and you do first the tensor product between 2 and then you do the scalar product.
That is, the integral of the form omega AB corresponds to the surface integral of the displacement field as A. Footnote 29.
Let's go to the footnote.
Note that, strictly speaking, while omega AB is a tensor, epsilon ABC and SA are not. Relationship 1.103 then is valid only if we choose position, momentum, and time as variables. Yet, as we will see much later, we can change the position variable and time variable and still have the same expression by redefining momentum and energy appropriately. Okay. In phase space extended by time, then, omega AB quantifies both the number of states over a surface and the flow of the displacement field through the surface. Under assumption dr, determinism and reversibility, this works because we have one and only one evolution for each state. Therefore, quantifying the number of evolutions that intersect a given surface is the same as quantifying the number of states that flow through them. Yeah, that makes sense.
One striking feature of the vector potential theta A is that it is fully characterized by a single arbitrary component, the time component minus h. The magnetic vector potential A sub I instead is characterized by 2 arbitrary components. What are the exact physical conditions that allow that to happen? Okay. I'm gonna continue because that was short.
Sure.
Suppose that SA is a divergence-less field, then we can write it as minus the curl of a potential. Vector potentials are defined up to the gradient of an arbitrary function that is up to a gauge, since the curl of the of theta plus the gradient of some scalar function is equal to the curl of theta. We can choose the function f such that the derivative with respect to the partial derivative with respect to momentum of this function is minus theta, the momentum component of theta, right?
Yeah.
And therefore we can set without loss of generality the momentum component to 0. Okay. So far, this procedure can be applied to any potential of a divergence-less field. However, the displacement field SA is particular in that its time component is unitary. That is, states flow at a uniform rate and time. Therefore, we must have, so that would be the...
So we're basically calculating, so we know that theta is the vector potential of S. So we calculate the T component, which is this. And we already know that theta P was 0. And so we just have this term. So it's plus partial Q theta Q. And we know that this has to be 1.
So integrating the relationship, we find that theta Q is P plus C of Q and T, where C of Q and T is an arbitrary function. We can choose C of Q and T equals 0 without loss of generality, since that arbitrariness corresponds to a choice of gauge. In fact, we can choose f of Q and T such that partial Q of f equals minus C of Q and T. Given that partial P of f of Q and T equals 0, this will not impact the previous arbitrary choice of theta p equals 0. And we have equation 1.108.
Right, so we basically fixed both components. We just have the only component that is free is the time component now.
At this point, we simply rename the last component to minus h and have equation 1.109. The form of the vector potential then is set by the fact that the flow of SA is both divergentless and uniform along the time direction.
This discussion tells us exactly what theta A is in the case of a single degree of freedom. It is the potential of a displacement field SA, or equivalently of the form omega AB. Since we are in the single degree of freedom case, assumption, determinism, and reversibility is enough to recover Hamiltonian mechanics. And this is the same in the extended phase space formulation. Maybe I'll finish this section.
Yeah.
We also learned another thing. The Hamiltonian is the time component of the potential. Therefore, it is not a scalar. That is, if we made a change in the time variable t hat equals t hat of t, we would have h hat is minus theta t hat. Transforms like a scalar only under purely spatial change of variables.
Right, so it's a scalar only if this is 1, which means that you're not redefining time. Okay, so the cool thing is that the fact that Hamiltonian is, if you look at this, if you studied, special relativity or general relativity, this already looks like a momentum vector, right? We have the momentum, and then on the time component, you have the minus h, you have the energy, minus the energy. This is exactly what you have in relativity. We haven't done any relativity yet. We just extended phase space with time and made it work, and this just pops out. Right? It's to me, it's absolutely cute that this happens. And then the other thing that it's important to me is that we can do all these reconstruction because we can go component by component and see what happens. And a lot of the time when you do differential geometry, you work with this representation that are coordinate independent. You don't see the coordinate, you don't see the components. And it makes it basically impossible to understand what's happening, because we see the time component is special. It does things differently than the space and the momentum. And the understanding of that we can represent this potential as essentially the momentum, the energy momentum vector, it's something that you can only see if you work in the component. So this is where I think that sort of the way that things are formulated currently in mechanics and in relativity also, that the component free notation is well, at least on the math side, it's downplayed. It's more prevalent, the component free notation. I think it's a mistake. You really don't see the physics. So, and this is going to be even more clear now that we do the interpretation of the action.
Right, Lagrangian and action. Now that we have seen that now that we have seen what theta A is, we can go back to the Lagrangian and the action. Suppose that we have a path gamma, not necessarily an actual evolution, that proceeds along the time variable. That is, we can write gamma qit, pit, and t, right, and d gamma as d psi a, dt psi a, dt. Let's see.
It's clear what's happening. So this is just a curve, right? So the curve is parameterized by t, and you give you the position, the momentum, and the time. And then you're just doing the infinitesimal displacement, which is the infinitesimal change along the curve. Since t is, you see that t has two functions here. It's both a variable, but it's also the affine parameter. It tells you how you are going through the curve. And this basically dual use of t might be confusing, but that's exactly what allows us to write this expression.
Okay. Where we use the time variable as its affine parameter. Note that in this case, the displacement is along the generic path gamma, which is not necessarily an actual evolution. Therefore, dt psi a is equal displacement a if and only if gamma is an actual evolution of the system. For a generic path, we can write Lagrangian as the Legendre transform of the Hamiltonian, and that gives you theta a dt psi a. And you write here the action in gamma is the integral over gamma of L dt. That's the standard way. You substitute what's above, and that gives you integral over gamma of theta a d psi a, which is integral over gamma of theta d gamma. This tells us that the action along path gamma is the line integral of the vector potential theta a of the form omega ab. We now have a precise geometric characterization of the action of the Lagrangian. As for the physics, it tells us conclusively that both the Lagrangian and the action by themselves are unphysical. That is, the value of the Lagrangian at a given position, velocity, and time, or the value of the action for a given path is not a physically meaningful value. The vector potential is not a physical quantity. It depends on a choice of gauge, which does not correspond to a physically well-defined object.
Right. So this is basically the key to understand what all these things are and how they're related, right? So this is just the point that this part here is the Lagrangian. It's essentially the product between these two elements. And as we saw before, the theta A is a vector potential, so you have the freedom of change in the gauge. Therefore, the Lagrangian is not unique because, as we saw before, we could change the Lagrangian. Well, now we know why we can change the Lagrangian, because it has a vector potential inside. So you change the vector potential, you make a gauge transformation, you have changed the Lagrangian, but you changed the gauge, so you haven't changed the physics. Oh, it's a whole section afterwards. So.
Oh, sorry, it's my turn. Yeah.
Yeah.
Okay. We are now in the position to understand why, as we have seen before, the Lagrangian for a given system is not unique. It depends on the vector potential, and the vector potential is not uniquely defined. We can see how the change of Lagrangian corresponds to redefining the vector potential, as then we just add the arbitrary partial derivative. We have our Lagrangian.
Yeah, so this is basically, that's the standard thing. This is a vector potential. We take a scalar function and we take the derivative. Note that this in principle could also be a function of momentum, right? But right now I'm just showing that this is exactly the transformation that we had before. So what you're basically doing is taking the derivative of this. So this is the original Lagrangian. Now we have a new Lagrangian with theta changed. We are just changing the vector potential. And we can write this as the original Lagrangian plus this gradient of S time the displacement contracted with the displacement field, right? And now we can write this into the two parts, right? We have the part that is for position and the part that is for time. And you now basically take this partial derivative and you put them out, so you get the partial derivative out of time, and you get this expression. So this dt is 1, this is the partial derivative in time, and this is just the partial derivative of f with respect to position times the velocity. And if you look at what we saw like half an hour ago, that's exactly the type of transformation somewhere here. There you go, right? Where we were redefining the Lagrangian. So this thing is precisely because L has a vector potential, and we are just making a gauge transformation. So we can go back to where we were, which was here. So I don't know who's next.
Okay. I can go. But if the action and the Lagrangian are unphysical, how can we use them to derive the laws of evolution, which are clearly physical? Note that the laws are not expressed in terms of the action, but in terms of the variation of the action. Let gamma prime then be a small variation of the path gamma with the same endpoints. Note that gamma and gamma prime form a closed loop. Take a surface sigma that is enclosed by that boundary, and we use Stokes' theorem.
Okay, so you make the variation of the action along a path, right? Which is the variation of that integral that we had before, which is the variation of the line integral of the vector potential. The variation of the line integral is basically the integral along gamma minus the integral along gamma prime, which means that this is essentially the integral of over the contour of the surface that it's between the two paths. So the two paths make a closed loop. There is a surface in between. The variation of the action is simply the integral over the contour. And now you can use Stokes' theorem that basically tells you that the integral over the contour is the integral of the curl inside the surface, or better, of the exterior derivative. But we saw that the exterior of derivative was omega, and now this is the integral of omega.
And then what's that Greek letter, eta? Is that it?
So eta is the displacement essentially from gamma to gamma prime. Right?
Okay.
So you think that you're going through gamma, right? But then you're making the surface integral right now. So when we go from here to here, now you're not only having a displacement along the border, you also have a displacement along the surface. You're going inside. So this is the displacement inside the curve.
Okay. So where d eta b is the displacement of a point from gamma to the corresponding point on the variation, gamma prime. The variation of the action then corresponds to the surface integral of omega ab, which is physical. Geometrically, it corresponds to the flow of evolutions through the surface enclosed by the path in this variation. Note that because the flow is divergenceless, it does not matter which surface is chosen, since all surfaces that share the same boundaries will correspond to the same flow. This is a striking observation. While the action is unphysical, its variation is physical.
We now are in a perfect position to fully understand the principle of stationary action. This states that actual evolutions are given by paths for which the variation is zero. That is, the area integral sigma of omega AB has to be zero for all possible displacements in theta. This means that in eta, sorry. This means that we must have omega AV contracting displacement equals zero, since the displacement field is the only degenerate direction for omega AB. That is, we must have d psi A equals SA dt. In other words, the paths that make the action stationary are exactly the paths whose tangent vector applied to omega AB returns zero.
So that's the
Geometrically,
math. Yeah, that's the math, and now we go for the geometrical interpretation of this.
geometrically, if a path gamma is an evolution, it will always be tangent to the displacement field Si. If we make a small variation gamma prime, the two paths will enclose an infinitesimal strip sigma, which will be tangent to Si as well. Therefore, the flow of Si's through sigma will be zero. Given that the flow through sigma is minus the variation of the action for all evolutions will be 0. Conversely, if a path is not an evolution, at some point its tangent will be different from the displacement field. Therefore, we will be able to find a variation gamma prime for which the surface sigma will catch some flow. That is, we will have a variation of the path for which the variation of the action is non-zero. In other words, the action principle is a geometrically roundabout way to ask for those paths that are always tangent to the displacement field Si, which is divergenceless and has constant flow in time.
Note that the geometric and physical interpretation we have given to the Lagrangian and the action lives in the extended phase space, which is part of the Hamiltonian formulation. In fact, the only place where we need assumption Ke is when we want to write Pi dt Qi minus h as a function of velocity instead of momentum. The integral of the vector potential and its variation, in fact, can still be written even in terms of momentum, and therefore the geometric and physical characterization of the principle of stationary action applies for all Hamiltonian systems, not just the Lagrangian subset. In other words, the principle of stationary action is really more a property of Hamiltonian mechanics than Lagrangian mechanics. The only difference is that in Lagrangian mechanics, since assumption kinematic equivalence applies, it can be expressed purely in terms of kinematic variables.
So since we have done the hour, I would not venture to the multiple degrees of freedom. We'll leave it for next time. Even though it's short, I don't think we can do it because it's going to be more complicated. If there are questions, either from you guys or from the chat, we can answer question and have discussion. And if not, we can stop.
I'm still trying to understand, like, I don't completely geometrically understand what our like simple active form does when we extend it to time. Like, I understand, like, for phase space it was counting states, and it still does that if we have two vectors which are like purely in phase space with time component 0. But at this point, I don't completely understand what the symplectic form represents for vectors that do include the time component.
So you can imagine that since we went from just states with states and time, now the objects that we are describing are no longer states but evolutions. And so while before the symplectic form was just counting states, this new extended things that is technically not a symplectic form because it has a divergence that is degenerate, is essentially counting the flow, counting the trajectories. And so now it makes sense that if I am, at if I take a slice that it's at equal time so that I get a degree of freedom, of course, I will need trajectory to go through it because trajectory has to go through every slice, right? I can't have trajectory that goes along a degree of freedom. It would not make sense, right? But if I take a slice that is parallel to the direction of the flow, then that thing is not gonna catch any evolution.
Yeah, I think now it clicked for me. Thank you.
Good. Yeah. And again, if I had more time and resources, I would add pictures in this that would show this. But yeah, that's the thing. We went from points to essentially word line. If you think about it in relativistic terms, these are already word lines, except they're not just in space; they're also in momentum. And the kinematic equivalence is precisely that. Like if you have a word line in just space-time, you know that word line corresponds to exactly one row word line in position momentum m time. right? And if you don't have kinematic equivalence, since you can't reconstruct the momentum, you just know the velocity, that's not enough.
Makes sense for me.
Hello, Isaac Lewis. If there are questions from the chat, I'm happy to get them. And if there are people in the chat that are interested in participating, they can send me an email. I can put them in the Discord group and all of that. And don't seem that there are any questions, so I would just stop it here, and we'll see each other next week.
Nice week.
Bye, guys.
Bye-bye.
Yeah, have a great week. Bye.
You too.